Hello everyone, I'm Chunyang Wang from Nanjing University. Today I will talk about counting random k-set near the satisfiability threshold. It is a joint work with Chen, Aditya, Quan, and Yitong. Constraint satisfaction problem, or in short, CSP, is one of the most fundamental problems in computer science. Let V be a set of variables, each with a finite domain QV. Given a set of constraints, with each constraint C defined on a local subset of variables, that maps each configuration on these variables to either true or false. A CSP solution is assignment to all variables, such that all constraints evaluate to true. A random CSP is a CSP whose constraints are generated randomly with a fixed constraint to variable density alpha. This problem can also be interpreted as dilute mean-field spin glasses in statistical physics, and therefore attracts a lot of attention in both theoretical computer science and statistical physics. Here are two important examples of CSPs, k-set and hypergraph Q-coloring. In k-set, all variables are Boolean, and each clause can be interpreted as a constraint defined over k variables. The solution is assignment to all variables such that each clause evaluates to true. In hypergraph Q-coloring, we have a k-uniform hypergraph H and a color set Q for each vertex. The solution is assignment of Q colors to each vertex so that no hyperedge is monochromatic. We can consider random k-set with a fixed density alpha, where there are alpha n clauses, and each clause is uniformly chosen from all size k subsets of 2n literals. Also, in the case of random hypergraph Q-colorings, the underlying hypergraph is the Erdős-Renyi random hypergraph, which is a uniform random hypergraph from all k-uniform hypergraphs with n vertices and alpha n hyperedges. Most of the attention towards random CSPs has been focusing on random k-set. A central question is that how the random k-set behaves as the density alpha changes. Theoretical computer scientists focus on algorithmic aspects, that is, the tractability of the following three questions with increasing difficulty. When does a solution exist with high probability? When can we find the solution efficiently with high probability? And when can we almost uniformly sample a random solution or approximately count the number of solutions efficiently with high probability? Meanwhile, statistical physics concerns the geometry of the solution space, basically regarding the connectivity and the correlation of the solution space. Here, this diagram depicts a heuristic graph of the phase transitions of the solution space regarding the density alpha. So the solution space starts out with a unique cluster of solutions. After the uniqueness threshold, the solution space is dominated by one large cluster. After the clustering threshold, the solution space scatters into exponentially many clusters. After the condensation threshold, the solution space is dominated by a few large clusters. Finally, after the satisfiability threshold, no solution can be found with high probability. A major question is that where these thresholds are located at. This diagram was depicted from heuristics done by statistical physicists, by which time no rigorous proofs are known. Recently, a paper by Ding, Sly, and Sun formally gives the explicit satisfiability threshold. In 2008, Cleopas and Koja-Ogland showed that the clustering threshold is approximately 2 to the k log k over k, while Koja-Ogland shows that an efficient search algorithm exists with high probability when alpha is 1 minus OK1 2 to the k log k over k. Also, recently, Bressler and Huang have proved a lower bound that a class of low-degree polynomial algorithms are destined to fail when alpha is below a constant times 2 to the k log k over k. All these results seems to suggest that the algorithmic threshold probably would coincide with the clustering threshold. So, our focus is the sampling counting threshold of random k-set, which is under what densities can we efficiently sample or count solutions to a random k-set. This problem is somewhat related to estimating the free energy in statistical physics. A first progress for this problem was by Galanis, Goldberg, Guo, and Yang, which gives an F-Peters for this problem under the regime alpha less than or equal to 2 to the k over 300. Here, the tilted inequality means we only care about the exponent that hides polynomial factors of k. Two recent works by Chen, Galanis, Goldberg, Guo, Herrera, Poetus, Manny, Moitra, and Wang have improved this exponent as well as giving a fast sampler. To date, the best threshold of sampling counting random k-set was located at alpha less than or equal to 2 to the k over 3 by He, Wu, and Yang. Yet, there remains an exponential gap between the sampling threshold and the satisfiability and algorithmic threshold. Therefore, a natural question to ask is that, is counting sampling random k-set tractable up to the algorithmic threshold? In our work, we answer this question affirmatively. We show that counting sampling random k-set is tractable when the density is below 2 to the k over a polynomial of k, showing that counting sampling for random k-set matches the satisfiability threshold and the algorithmic threshold at the exponent. So this is our formal result. When the density parameter lies below 2 to the k over a polynomial of k, then with high probability, we can efficiently draw an almost uniform random solution, or deterministically estimate the number of solutions, both within a polynomial time. Our result also applies for random hypergraph colorings. We present algorithms for efficiently counting and sampling proper Q colorings of random K-uniform hypergraphs up to densities Q to the K over a polynomial of K and Q. Before delving into the techniques, we can first compare our results with the worst-case bounded degree CSPs. Note that a random k-set formula with density alpha has an average degree of k alpha, making it comparable to a k-set formula with maximum degree d equals to k alpha. Up to date, the best result for sampling k-set is by Wang and Ying, effectively up to 2 to the k over 4.82. Also, there's a lower bound of 2 to the k over 2, which demonstrates that the sampling and counting problems are computationally much harder than searching for bounded degree CSPs. A similar phenomenon occurs for hypergraph colorings as well, while there is a separation between sampling and searching for the bounded degree case. Our result for the random hypergraph colorings doesn't exhibit this separation. Overall, our findings demonstrate that for random CSPs, the sampling and counting problems are not significantly computationally harder than their satisfiability and algorithmic counterparts. So, we then illustrate our techniques. A canonical approach to understand the solution space of the random k-set by statistical physicists is through the cavity method, which studies the influence on the solution space by flipping one variable and sees if there exhibits a decay of correlation or not. One important notion of decay of correlation in statistical physics is replica symmetry, which refers to the idea that two uniformly chosen variables are nearly independent. This replica symmetry property is conjectured to hold up to the condensation threshold, which has been verified on a few other models. Another stronger notion of decay of correlation is non-reconstruction, and has been shown to be a necessary condition for the rapid mixing of global dynamics. This non-reconstruction property was conjectured to hold up to the clustering threshold. However, both two notions above are established through empirical studies in statistical physics using heuristics, and seldomly rigorously proved. In our work, we managed to show a decay of correlation property in the sense of so-called coupling independence, which is essential for our sampling and counting algorithm. We show that for two random k-set instances that differ in one constraint, there exists a coupling of their uniform distribution over solutions, such that the Hamming distance between the outcomes has an exponential decay. This is, in fact, a stronger notion of decay of correlation, and it formally implies both replica symmetry and non-reconstruction in our considered density. The way we establish the property is inspired by the recently developed recursive coupling procedure for bounded degree CSPs by Wang and Ying. We first illustrate their coupling. We consider phi as the CSP instance on the right, which is a two-coloring instance where each red constraint must contain one red variable, and each green constraint must contain one green variable. On the left, we have a CSP instance with one less constraint. We want to couple the uniform distribution of these two. Note that we can decompose the distribution on the left using the law of total probability according to whether the additional constraint is satisfied or not. We can therefore proceed as follows. With this marginal probability, we couple μc with μc. Otherwise, we couple the distribution for the left instance conditional on the additional constraint being violated with μc. Note that for the former case, we have two identical distributions, which can already be perfectly coupled. So we consider the latter case. Note that here, the condition that some constraint is violated forces the assignment of variables on it. So have these variables fixed for the instance on the left. We now again apply the law of total probability to sample the outcome of these variables for the instance on the right. Let's say we have this sampled outcome. What's going on after the assignment on these variables is that we can now simplify the formula. Now we are generally faced again the problem of coupling two sets of constraints, differing in possibly one or more constraints. What we will do is to recursively apply the previous procedure, each time picking any constraint in the discrepancy set and recurse until the sets of constraints become the same, which will eventually happen after all variables have been assigned. So this gives their coupling procedure. So here is the illustration. The coupling might go like this, and we have again assigned, and after the simplification, the two sets of constraints became the same, and the coupling now ends. Okay. So this is basically the formal coupling procedure, and it shows what we described earlier. Okay. Now we jump to the ideas of the analysis of this coupling procedure. So in the bounded degree case, a good thing is that when the minimum size of each constraint is large enough with respect to the maximum degree, we have good control over the marginal probabilities. One challenge for this is that, however, the size of each constraint may degrade after each step of the coupling, making this property difficult to apply. The saving grace is that the random choices involved in this constraint-wise coupling procedure can be explicitly identified by two independent samples of the corresponding distribution, such that sampling by the marginal distribution is equivalent to revealing local information of the corresponding samples. This is, in a nutshell, the principle of deferred decisions. This is what helps us to overcome the previously mentioned challenge and constitutes most of the ideas in the coupling by Wang and Ying. So their coupling can be interpreted in this way, such that all randomness are generated through two independent samples, which we have good control over. Then we can use this property to analyze the coupling. Here, two challenges still remain when we use this coupling to the random CSP setting. The first is that for random CSPs, high degree variables exist. The second one is that the original analysis for bounded degree CSPs only leads to an exponent of 2 plus 0.1, while we improve this exponent down to 1. So, for the first challenge, we apply some traditional methods of separating high degree variables. By collecting high degree variables and constraints that contains too many high degree variables, we find that with high probability, these high degree variables are well behaved in a sense that they only constitute a small portion for any logarithmic sized connected component. Therefore, we can handle the problem as if we are in the bounded degree case. So for the second challenge, the way we analyze the coupling procedure is to use a so-called witness argument. Formally, we will show that if the coupling runs for too long, then we can find a combinatorial structure, which we call witness, that occurs with a very small probability. So, in the paper by Wang and Ying, the witness they choose is a combinatorial structure called two-tree, first invented by Long. In our work, we use a denser witness called witness tree that resembles the witness tree used by Moss and Tadash for the algorithmic Lovász-Luch lemma. As an example, suppose the coupling procedure assigns variable to three constraints. This is the set of constraints for the example we gave earlier, which are connected in the dependency graph. the combinatorial structure in the paper by Wang and Ying selects a maximal independent set of it, whereas we construct a denser tree structure encoding all constraints, and hence leading to the improvement. The reason we are able to make this improvement is due to the good expansion property of random instances. Let's then briefly discuss how to turn this correlation decay result into algorithms. Note that this coupling procedure is idealized. We cannot actually run it because it involves estimating some non-trivial marginal probabilities. However, the go-to method is to use linear programming that encode coupling errors to bootstrap the marginal probability. This is the method invented by Moitra, applied in quite many works for sampling counting boundary degree CSP solutions. Though yet no formal general theorems have been established, the rule of thumb is that when you can prove the existence of a locally constructive coupling as the one I'm formally described, then you probably can turn the analysis into a linear program that can bootstrap the marginal probability. And to finish our argument, we will utilize the constraint-wise self-reducibility of CSPs. By decomposing the constraints one-to-one, we can establish efficient counting sampling for CSPs using only marginal estimators or a dynamic sampler that can update samples according to the desired distribution. So, as a summary, we present polynomial time algorithms for approximate counting, almost uniform sampling random k-set solutions with high probability under regimes alpha less than or equal to 2 to the k over poly k. This regime is near the satisfiability threshold and also bypasses the lower bound of boundary degree k-set, showing that random instances are computationally easier to sample. Our result also gives formal proofs to several correlation decay properties such as replica symmetry and non-reconstruction under the same regime. So many open problems still remain. The first one is that we still don't know if the connectivity property holds under this regime. The second one is the exact sampling threshold for random k-set. Our current guess is the clustering threshold, which coincides with the guess of the search threshold. The last one is our current algorithm has a running time where the exponent of n depends on the parameters such as k, alpha, and q. We wonder if we can design sampling algorithms with a fast running time. That's the end of this talk, and thanks for listening.